Good morning. This morning I'm going to derive a result. It's the commutator of the covariant derivative while acting on a vector. This produces a structure known as the Riemann tensor. Don't worry about the name of it. Actually, you'll find me calling it Riemann tensor all the time because all my life I've mispronounced it. It's the Riemann tensor. But I will say Riemann because I won't remember the proper pronunciation. Okay? It's coming up. I'm not going to write the name on the board just yet. All we're doing is looking at the covariant derivative commutator d nu operating on the vector a lambda. These are the components of a vector. A lambda d nu d mu. In other words, the commutator. Now straight away when we have a commutator, we'll see that it's going to have an anti-symmetry in those two components. And that's going to be something we will use later on as we study the symmetries of the Riemann tensor. Okay? And the Riemann tensor will generate the Ricci tensor, and the Ricci tensor will generate the Ricci scalar or curvature scalar. Okay? We go from 4 indices to 2 indices to none. Okay, so if you like a rank 4 tensor to a rank 2 tensor to a rank 0. So normally I do all the derivations live, but because this one, when I did it first, took me 45 minutes to get the whole thing right. When I corrected a couple of mistakes, I decided to put it on the board first. And I actually shortened it because I used 2 whiteboards the last time when I derived it live. And I only get 28 minutes for this presentation. Anyway, it makes sure I don't make mistakes. I may have made an index mistake here, I don't think so. I'll write down the correct result in the end anyway. So we begin by just looking at the commutator, d mu, d nu. We're going to get this object here. Ignore that for now. Ignore that completely. So we'll look at one term at a time because there are too many indices involved. Then, when we work out one term, term 1, all you have to do is reverse the mu and the nu in your calculation. We'll see. So the first term, d nu, acting on a lambda. We'll write the covariant derivative in our old-fashioned way. Semicolon. It's the same as taking the first derivative d nu and then following up with d mu. Another way of writing it is like this, but this is the shorthand notation. Now, this is going to be a tensor, the derivative of a lambda with respect to mu covariantly. Okay? This is a contravariant vector. We'll just call it t mu, t lambda mu, because it's easy to see where the structure lies when we do that. So t lambda mu, what does it look like? Take the covariant derivative of the vector and go back to our lecture on covariant derivatives. We see that it has the structure partial derivative of a lambda with respect to mu plus the Christoffel part, right? And the Christoffel part is summed over these indices. Yeah? Because this is an upper index. If it was a contravariant, there would be a minus sign here and a lower. And we'll have a contravariant coming in down here somewhere. Okay, so the structure of these guys here, I wrote down earlier on as well. For this result, we don't need to know it. Okay? So now we're still looking at the first term. We'll take the covariant derivative of the tensor. It has 2 indices. So we have to hit the lambda first with a Christoffel symbol. We have to hit the mu next with the Christoffel symbol. And we also have to include the partial derivative. In other words, this term here, when we take the covariant derivative, has 2 indices. It has a partial derivative part plus the contravariant index part and the covariant index part. And if you go back to my covariant derivative lectures, you will see that the covariant one is negative and the contravariant one, the upstairs one, is positive. So, that's term number 1, is it? That's term number 1. Now term number 2 is exactly the same thing, but we reverse the mu and the nu. Wherever there's a mu, we put a mu, and wherever there's a nu, we put a mu. Mu, nu get reversed. We reverse them. Okay? So the terms look the same, just with the indices reversed, because here's the nu and the mu, and now down here the mu and the nu is reversed. Here's the mu and the nu, and here's the nu and the mu here. Now, very conveniently, here's what happens. The gammas are symmetric in the mu and the nu so that we can cancel two terms straight away. We want to cancel as many terms as we can in long calculations. So we're simplified now so that we can write down the 1 plus the 2. The 1 plus the 2 is the two partial derivative terms with the mu and the nu, and then the nu and the mu just reversed. See, you can follow through all this in the derivation yourselves later. Keep the video close by. It's very easy to get lost because if you didn't take this step, if you don't follow these steps, it doesn't work out quite right. Okay, and we'll add in the two gamma parts. So now we have 1 plus 2. Now, of course, this T mu nu has this structure up here. And we have to put it in because we have to operate on these terms. So, what's the covariant derivative of this T mu thing altogether? Covariant derivative of this, right? Well, it's going to be the covariant derivative of the mu, the mu part with the nu, and the nu part with the mu. Two partial derivatives first, followed by this structure, the gamma part. In other words, the whole tensor partialed first, and then the gamma part on the whole tensor. See? And one is contravariant and one is covariant. So get your head around that. It's only letting your fingers do all the calculations. We can't make a mistake. Now we have our second cancellation. Very conveniently, our second cancellation works because the partial derivatives commute. dy by dx is the same as dx by dy on any function. Yeah? Well, here's the situation where you have a mu differentiated with respect to a nu, and a nu differentiated with respect to mu. So, these two terms cancel, and they're gone. Yeah, right? So we'll just write down what's left now. We've had 4 terms cancel. We have the partials up here, and we have the partials down here, and we will see that all partials will cancel. This will turn out to be a structure whereby it's just a product of something. All partials will cancel for everything. Well, except for the connection, the Christoffel partials. So we write down this one and this one. Here it is here. And here it is here. Now we have to take the derivative of this part and then this part. There's that part, and there's the vector part. We have to take the derivative of this one followed by this one. There's the Christoffel part followed by the partial part of the vector. And then we write down just our products what are left. Well, our products, where are they? I missed something? If I missed something, you can check it out at home, but I don't think so. All partials cancel anyway. So let's see, what are the product terms? There's this one and this one. Now we go to our other cancellations. Here is a partial with respect to mu, and here is a partial with respect to mu, multiplied by the same structure, lambda sigma nu. Lambda sigma nu though, but with a negative sign. So we label this term as 2, and it cancels. This one and this one cancels. All partials will cancel when there's a partial derivative of a vector, anywhere, okay? So if I made a mistake, there's some partial derivative of a vector here, that's going to cancel, and that's going to cancel. It's going to be gone if I left them out somewhere. I don't think I did that. Okay, so now we're left with products. Product here and a product here. So I'm just going to write them out. Here's the first two products with a sigma in there. Here and here. And here's the second two products with an epsilon. See? The second two products with an epsilon. Now they have the same kind of structure. So what we're going to do is this. We want to make everything look the same. We don't need a sigma and an epsilon. So we're going to make everywhere there's an epsilon we replace with a sigma, and everywhere there's a sigma we will replace with an epsilon in this term here, just this one, where I put the reds. If sigma becomes epsilon, epsilon becomes sigma. Sigma becomes epsilon, sigma becomes epsilon, sigma becomes epsilon, and epsilon becomes sigma. So now we have a product of a vector with components sigma. We can swap those because they are summed over indices. When you have summed over indices, you can make them any index you want. You can make the summed over index anything you want, right? Because this is just a summation convention. That's all that's going on there. So now let's look at what we've got. We'll take out a common factor of the A sigma. The A sigma. And we write down all these terms. There's a gamma with a derivative, and a gamma with a derivative, with the mu and the nu, and then the nu and the mu swapped. Okay, antisymmetric in mu and u. We'll carry that always with us. Same thing here, and the same thing here. Antisymmetric in mu and u. And that's going to be a result of our tensor. So now we'll call this whole quantity in brackets R lambda sigma mu nu. Alright? Now that's the way I've written it. Somebody else might write it with a slightly different convention. So R lambda sigma mu nu equals A sigma times A sigma is equal to the covariant derivative commutator on A sigma. So let's write that down completely. Now, because of the symmetries of the Riemann tensor, I can move these sigmas and around in certain ways. So I'm going to write it in a more conventional way, as some text wrote it. I can't remember who wrote it that way, I guess. No, I don't have it, so I just have to write. I don't have any notes. It doesn't matter. I'll use mine. Now, all the time we want to get the second term with the negative sign. We just swap the two indices mu and u. And that's what we get. Here is the Riemann or Riemann tensor. It's the object you get. We can't be writing down these terms all the time, so we put in a shorthand notation, or lambda sigma mu nu. Now straight away we've seen that the two indices, when reversed, will swap the signs of all of these terms. In other words, antisymmetry in the two indices. Okay? Now I could have defined it with the lambda and the sigma down here, but I didn't. I leave it that way. In the next lecture I might change the actual definition. So we have antisymmetry in the indices nu and mu. And we have defined the Riemann tensor or Riemann tensor. Now, it is possible in the tensor calculus world to sum over a contravariant and a covariant. In other words, an upstairs and a downstairs in this index. So we can write them both as mu's or lambdas. This defines a new tensor, which we call the Ricci tensor. Now, the Ricci tensor is symmetric in the two indices, sigma and mu. Now we can contract over the mu and the sigma, which is just like multiplying by a metric tensor, contravariant indices upstairs, and then we get a scalar, all indices summed, and this is called the Ricci scalar. Curvature or Ricci scalar. So that's where we're going. All we did with this so far was we started off with the covariant derivative. We have yet to prove that the gamma has a certain kind of structure, the Christoffel symbols, but I wrote them down what they are. So everything is just related to covariant derivatives. We want to maintain a derivative that is a tensor after general coordinate transformations, and all this stuff comes out. I never mentioned manifolds. I never mentioned differential forms. I never mentioned anything. We want to keep this as simple as possible. Big mathematics will cloud the issue. If you want to go into the detail, a great book is by Wald. But you have to have things under control. It'd be better to learn the theory of general relativity first before you start going into those big books. Do I have Wald here? I do have it somewhere in a different room. I'm not going to run off and look for it now. Mr. Thorne and Wheeler, that really clouds the issue in a serious way, okay? And they get sidetracked in all sorts of different other things. and they use strange language. I don't recommend it. I'm sorry for the people who publish it. It just looks great because it's so thick, but it's too thick. And I walk in here straight away, and they're going into details that you do not need if you want to just understand the basic ideas of general relativity, which I actually gave you in qualitative form at the very first lecture. In a while we'll be able to put mathematics onto a lot of that qualitative stuff. Okay. Now, the Ricci tensor is also called the curvature tensor, and a necessary and sufficient, both words necessary and sufficient condition for a space-time to be flat is that the metric tensor is 0. Okay? Now in the next class we will discuss the symmetries of the metric tensor. The Riemann tensor. The symmetries of the Riemann tensor are very important. And some shortcuts. We'll show some shortcuts for calculation of those results. Alright then, that's enough for this one. Next one is coming up.